And he was there for 4 years till 2023, and then he made a short excursion to the east to serve as assistant professor at St. Lawrence University in New York, but I think he decided he really wanted to be out west. So when we had a job opening in our structural geology and mapping program, and Mark was applied, and we're very grateful that he did, because we're very happy to have him. He's worked on lots of different things that are somewhat similar to what he's going to talk about tonight. Proterozoic orogenic belts in the southwestern U.S. And that's a very controversial topic, and I think Mark's going to wade into that. And personalities like, Carl Karlstrom and Phil Anderson, going back a ways, there's been a variety of opinions about how these things work. It's always interesting. And so, not that I've never been involved in it myself, I've just been a interested bystander, but it's an interesting field. He's done a lot of work in other sort of Precambrian works. He's investigated Mesoproterozoic and Cambrian tectonic evolution of Laurentia. To understand mantle plume and lithosphere interactions and lots of other different things. He actually has ventured into the Cenozoic a little bit and worked on the strain partitioning from the Denali Fault in Alaska, and I think is it in Alaska or Yukon? Just Alaska? Yeah. So, and the terminal suturing, the Wrangelian composite terrain. So he's done lots of different things. What he's working on now is high precision zircon geochronology and geochemistry to test models of Proterozoic massive type anorthosite petrogenesis. Sorry, I'm bangling this. Anyway, tonight he's going to talk about the Precambrian in central Arizona. He's done a lot of work on that before, and it is an interesting and controversial topic. So, Mark.
All right, thanks, Phil. So just a couple of quick disclaimers. My son started daycare last week, and for those of you whose kids are older and grown and you've forgotten about what that means, or if you don't have kids yet, it means that I gave them a lot of money and they gave me a virus. So I'm not at 100%, and I basically, Phil, asked me to give this talk a couple of weeks ago, and so I said, okay, I can dust off some things I worked on a while back. So it's kind of a rehash of a GSA talk or two that I've given in the past, and so I will be repeating that almost verbatim. So I'm going to be recycling jokes, and if you've seen any of this before, then just try to laugh at the punchlines as appropriately. But excuse me, yeah. Anyway. So that's what we're doing here. So I'm going to be talking about this this concept of crustal provinces. North America, one of the most well characterized continents on Earth. It's very very well studied, and in a very widely cited and sort of ubiquitous kind of model. We have the kind of core. There's a pointer here, it doesn't seem to work, but we got the core of the Canadian Shield, all these Archean cratons in Canada that form the heart of North America, or Laurentia, and then basically most of the lower 48 is largely thought to have sort of accreted in a series of orogenic pulses. I guess I didn't go all the way here, but basically a series of these sort of accretionary orogenic events that are supposed to have grown the continent, to the south, sort of present coordinates, and this is a pretty well ascribed model, right? The sort of Yavapai and Mazatzal provinces are these terms that pop up all the time in North America. If you've read anything to do with the tridal zircon geochronology in the last 20 years in North America, every single sample has that big 1700 MA peak, 1400 MA peak. There's just these kind of classic populations that are associated with these zones of crust that are shown kind of in green here. That's going to be the Yavapai province, and then in blue is the Mazatzal province. And so this is fairly widely ascribed. But despite the sort of prevalence of this model and the elegance of the figure here from Whitmire and Karlstrom, kind of depicting this generalized tectonic history. Despite what we see here with these nice sharp contacts between provinces, identifying sutures or actual structures that mark the end of one province and the beginning of another has been a persistent challenge. So usually if you sort of zoom in, we're going to zoom in a little bit on the western US. I got kind of a similar figure here. The Proterozoic rocks are shown in gray, so we mostly have the front range and the Rockies there, and then the Arizona transition zone are the two main sort of exposures in the western US of these Proterozoic belts. And so oftentimes what we see when we look in detail is that these province boundaries are depicted as gradational, or they're defined isotopically. But the problem is that depending on which isotopic system you might use to define a boundary, so that a lot of my PhD work was focused on the Mojave province and the nature of the Yavapai-Mojave province boundary. So if you use neodymium isotopes, if you use lead isotopes, if you use hafnium isotopes, all these different isotope signatures, yeah, there's a difference between the province, but it's not a sharp line that you can draw on a map to say, oh, on one side of this shear zone, there's evolved rocks, and on the other side, there's juvenile rocks. You have this kind of gradation. And then also in the sort of Yavapai-Mazatzal transition zone, you can see here in sort of southern Colorado and northern New Mexico, there's this sort of transition zone between those two crustal provinces, which is thought to be this zone of rocks that are Yavapai province age but deformed during the Mazatzal orogeny, that kind of thing. And so you get these sort of gradational transitions. So it's been a really hard thing to actually find these province boundaries. So I started thinking, well, why don't we go to sort of the original definition? If we trace back these concepts, in the literature, where do they first appear? And so these terms are sort of introduced and defined in the Arizona transition zone. So this little red box down here, we're going to sort of zoom in on this area next. Excuse me. So yeah, so we've got kind of a generalized, simplified geologic map here showing the main elements of part of the Arizona transition zone. So in that sort of deep purple color, we got sort of Paleoproterozoic plutonic rocks. In the sort of lighter purple color, we got sort of metavolcanic, metasedimentary rocks. They're Paleoproterozoic. And then I've outlined as well a couple of Paleozoic rocks and basalts and things from the recent rocks, just to kind of give us an idea here. But this is a key area that in 1987, Karlstrom and others wrote this seminal paper sort of summarizing the geology of this large area, a couple of 100 kilometers cross strike, of the Arizona transition zone, and trying to put together a coherent model to explain all these rocks they observed there. And they defined two provinces. The terms Yavapai and Mazatzal province actually didn't appear in the 87 paper. They were introduced later, but this is the kind of origin of those provinces. Basically, what was synthesized, or I don't want to say discovered, but what was put together in this paper in 87 was that citing differences in several different areas, differences in lithology, differences in age, differences in structural style across this structure called the Moore Gulch shear zone, which is this sort of northeast striking structure here that I've labeled, hopefully very obviously, there in the center of the map. And so basically, the rocks to the northwest of the Moore Gulch shear zone tend to be a little bit older. So they tend to be greater than or equal to about 1.7 billion years old. They tend to be a little bit more high-grade metamorphic rocks. You get sort of amphibolites, amphibолite facies or green schist facies metamorphic rocks. And deformed in a more ductile structural style, whereas to the southeast of the Moore Gulch shear zone, we generally see younger rocks, right, younger than about 1.7 billion years old, sub-green schist grade to green schist grade metamorphism throughout much of this area. and a difference in structural style that's a little bit more brittle in character, epitomized by the rocks of the Mazatzal Mountains, which are just this central area right here, where the Mazatzal fold and thrust belt is, rather than sort of a ductile deformation style, is a little bit more of an upper crustal kind of brittle structural regime. So citing these broad differences in rock type, rock character, structural style, all that, Karlstrom and others divided the region into two provinces. And so I wrote here that those would actually be named the Yavapai and Mazatzal provinces by Karlstrom and Bowring in a subsequent paper in 1988. All right, so in the 87 paper, they construct a generalized kind of cross-section through this area. So there is a slight bend in the section or break that's sort of along the Moore Gulch shear zone there, but basically if we go from the northwest corner to the southeast corner, we've got two cross-sections, two generalized cross-sections in the shown on the right over there. And so they took all this information along with the generalized cross-sections and tried to propose two end-member models that might explain these differences in rocks across this structure, the Moore Gulch shear zone. And so in the first cross-section, in the first kind of hypothesis, the rocks of the Mazatzal province, or what would become later the Mazatzal province to the southeast, are para-autochthonous with respect to the Yavapai province, meaning that they formed more or less in place, but they've been moved a little bit. And in Model 2, the Mazatzal province is completely allochthonous with respect to the Yavapai province, meaning that it formed elsewhere in space and time and was structurally juxtaposed during orogenesis. So basically, those are these two models that are proposed to explain the broad differences in rock types that we see in this area. And so if we look at these two cross sections, the white line in the middle shows the sort of surface, the current level of exposure, which is the same in both of these cross sections. The geology is the same at the current level of exposure, of course. And what's different is what we interpret above and below the surface. And so the first model, where we have a para-autochthonous Mazatzal province, essentially says that the rocks of the Mazatzal province, the classic, quartzites and things like the Mazatzal quartzite or, Four Peaks, these classic quartzites of the Mazatzal province, are deposited unconformably on top of the Yavapai province. Whereas in Model 2, they have been thrust up and over the Yavapai province, right? So they were formed elsewhere in space and time and then been thrust up and over the Yavapai province. All right, and so in this 87 paper, outlining these two hypotheses, they also outlined some tests that we could do to test these two models. And so basically there's three things that could be boiled down to test Model 1, the para-autochthonous Mazatzal province model. I should mention that Model 2, the allochthonous one, where the Mazatzal province formed, as some sort of arc terrain, out in space, is sort of the broadly accepted one, right? The idea that this is an accretionary origin where we've accreted exotic terrains was the sort of buzzword of the time. Excuse me. But so there's been a lot written about Model 2. So that Karlstrom and Bowring 88 paper presented arguments in favor of Model 2, and that those arguments have sort of been propagated, and that's been the dominant narrative going forward. But the first model, the para-autochthonous model, was actually never explicitly tested. And so there's three basic tests, I think, to test this para-autochthonous model. And they rely on, first, the relationship between sort of 1.75 to 1.72 billion-year-old metasedimentary and plutonic rocks that are on both the northwest and southeast side of the Moore Gulch shear zone, and as well as the relationship between the quartzites, the sort of 1.65 Ga quartzites of the Yavapai province. And then finally, of course, is the kinematic history that's recorded in the Moore Gulch shear zone itself. Despite this being proposed as the suture, right, the structure. Here on the Model 2 cross-section, you can see, I'm just going to kind of move over here. This here would be the Moore Gulch shear zone in this cross-section, where at the surface it marks the boundary between the Mazatzal and Yavapai provinces. No detailed structural analysis has really ever been done of this structure. So that seems like something that should be done if you think it's a suture. So basically I set out to test these hypotheses that were outlined in the Karlstrom and others 87 paper. All right, so basically Model 1 predicts, which again, Model 1 is the para-autochthonous model. It predicts that the basement of the Mazatzal province is unrelated to the Yavapai province. Oh, hang on, did I mix these two up? Yeah, all right, sorry, I'm mixing this up. So Model 2 is actually what I've written here. So the Model 2, the para-autochthonous, or the allochthonous model, predicts that the basement of the Mazatzal province is unrelated to the Yavapai province, that the Mazatzal province strata were derived from and deposited on top of the... All right, I got some wonky slides here. Let me back up. All right, this figure on the left, Model 1, para-autochthonous one. Actually, this should say that the basement of the Mazatzal province is related to the Yavapai province. This model would predict that they're the same thing. And then 2, the Mazatzal province strata should be derived from and deposited unconformably on top of the Yavapai province, and the Moore Gulch shear zone should be essentially a normal fault. Right? So we should have south side down, exposing a higher crustal level to the southeast. All right, Model 2, in contrast, predicts that the basement of the Mazatzal province is distinct from the Yavapai province, so that they're unrelated, that the Mazatzal province sedimentary rocks have no stratigraphic connection to the Yavapai province, and the Moore Gulch shear zone is a suture, so there should be sort of a south side up structural history recorded in that area. So these are testable things. All right, so so tested this in a couple of ways. So the first thing to do was to go and look at plutonic and metasedimentary rocks that are older than 1.7 billion years old that appear on both sides of the Moore Gulch shear zone. So again, rocks to the northwest of the Moore Gulch are mostly older than about 1.7 billion years old, and rocks to the southeast are mostly younger. But there are a handful of 1.75 billion year old rocks southeast of the Moore Gulch shear zone, notably here in the Gibson Creek batholith, which is into which the Pacinophyllite is emplaced. For many years since the mid-90s, it's been kind of known that there's 1.75 billion year old rocks there, although those data are not actually published. It's all cites an abstract in which there's no real data. But so the question is, are these 1.75 billion year old rocks to the southeast of the Moore Gulch shear zone, are they the same as the 1.75 billion year old rocks to the northwest of the Moore Gulch shear zone? So we can look at this question and test it in two ways, by looking at plutonic rocks as well as metasedimentary rocks. I think we're going to talk about metasedimentary rocks first. So this is, as you mentioned, this is some work that Mike Doe did as part of his PhD dissertation. Mike's a legendary Arizona person. I'm sure a lot of you know Mike Doe and probably have heard him talk before about some of this stuff. So some of this is from Mike's dissertation. But essentially we've got metasedimentary rocks that are older than 1.7 billion years old on the northwest and southeast side of the Moore Gulch shear zone. So we're going to compare them. So I've labeled their kind of locations in green here. We got 1, 2, 3, 4, 5, 6. The blue ones are to the southeast because they're part of the Mazatzal province allegedly. And so, all right, let's compare them. Well, we looked at detrital zircon geochronology in these rocks, and they're very similar. So to the northwest of the Moore Gulch shear zone, we have the Yavapai supergroup, which is a sequence of sort of interlayered metavolcanic and metasedimentary rocks. The metasedimentary rocks are generally metaturbidites and sort of immature clastic sedimentary rocks associated with kind of volcanic arc terrains. And in the Yavapai province, the detrital zircon signature is remarkably unimodal. and it's basically reflects the age of the plutonic basement. So we have these 1.74-ish billion-year-old unimodal age peaks, which are present in the metasedimentary rocks of the Yavapai supergroup. I should probably mention briefly, this is detrital zircon geochronologic data. We got age on the x-axis here, and think of these as like a histogram. So the taller the peak is at a particular age, the more grains of that age we dated. And so there's pretty much unimodal 1740-ish population in the Yavapai supergroup. And then if we go to the southeast of the Moore Gulch shear zone to the East Verde River Formation, which are metasedimentary rocks deposited on top of the Payson ophiolite in the Mazatzal province, we see the same thing, right? So we see this really strong unimodal detrital zircon signature, and it's basically reflecting the age of the plutonic rocks that intrude these things. It's the classic Yavapai province signature, about 1.74-ish billion years old. All right, so that's interesting. So they're basically the same, right? If we look northwest and southeast of the shear zone, the sediments appear to be very, very similar. We can also enhance this correlation with hafnium isotope data. I'm not going to get into the details of hafnium isotopes, but basically when you data zircon and you figure out its age, you can also figure out the hafnium isotope signature of that zircon, and it just gives you another another variable to compare things with. And so what this plot is showing is what's called a bivariate kernel density estimate of uranium lead and hafnium isotope data. So we got uranium lead age on the x-axis here, hafnium isotopes on the y-axis, and imagine a bunch of little points in here that would each represent a single zircon. But instead I've represented this as a bivariate kernel density estimate. So it's think of these fields as essentially the age and isotope composition fields of the detrital zircon data. And the hafnium isotopes tell us the same thing, right? They're the same thing. Got some, if you like numbers, you can put some numbers to these comparisons. A comparison metric equal to 1 would be a perfect match, right? And I see a bunch of 0.8s and 0.9s up there, so it's looking pretty good. All right, so the sediments are the same on either side of the shear zone, so I've changed these blues to greens because they seem to be exactly the same as the Yavapai supergroup, so I'm going to call them the Yavapai supergroup. All right, so now let's look at the plutonic rocks. So did the same thing, dated plutonic rocks and looked at their hafnium isotope signature on both sides of the Moore Gulch shear zone. Got a couple of samples from the Cherry Creek batholith, which is basically this whole chunk in here. So a couple of samples from the sort of western edge and the southern edge right near Moore Gulch. And also the Gibson Creek batholith over here, which again is underneath the East Verde River Formation. And so if we look at the age and hafnium isotope composition of those plutonic rocks, well, they're also looking pretty similar. So we got the Gibson Creek batholith, 2 or 3 samples from there that give about 1750 MA ages with epsilon hafnium values that sit right on depleted mantle here. Another characteristic of the Yavapai province in general, that very evolved, or excuse me, isotopically juvenile signature. And then in purple, we got the Ash Creek block plutons. So from here and here. And yeah, those are pretty much the same, right? And just for reference, I also put some hafnium isotope data from work I did in Grand Canyon from a master's thesis, which are the red diamonds, which are kind of hard to see because they're right behind the other rocks that we dated. And the reason that they're hard to see is because they're all the same, right? So same age, same hafnium isotope signature of the plutonic rocks that are older than 1.7 billion years old on both sides of the Moore Gulch shear zone. And if we compare the detrital zircon data to the plutonic rocks, right, so here again is that same KDE plot from before. So again, the green fields here, that's the fields of the detrital zircon geochronology data, and then we got the plutons sitting on top of that. So my interpretation of this is that the Yavapai supergroup, the metasedimentary rocks of the Yavapai province, are locally derived. and they're derived from the plutons that comprise the province itself. All right, so basically we see the same signature in the greater than 1.7 billion year old rocks on both sides of this suture. All right, so next we can look at the metasedimentary rocks that are a little bit younger, right? The sort of Mazatzal quartzite, the classic Mazatzal quartzite rocks. Again, if the kind of currently accepted model that the Mazatzal province is locked in its, is correct, then these metasedimentary rocks should record no record of the Yavapai province, right? But if the para-autochthonous model is correct, then they should be derived from the Yavapai province. So this too can be tested with the detrital zircon geochronology. And so this is going to be a big compilation of a number of people's works. So basically, in blue, in the sort of light blue color here, I've got the exposure of these sort of 1.65-ish billion year old quartzites. There's a key exposure up here in Chino Valley, which is in this part of the cross section. The Mazatzal Mountains itself, Four Peaks, and then Hess Canyon. All right, so, and just because they're really pretty and classic Arizona geology items, I got some really nice pictures here of these quartzites. John Spencer has worked on the ones in Chino Valley and cite his work, and then we got the classic quartzites of the Mazatzal Mountains. And then one of my personal favorites, the white ledges down here in Hess Canyon. All right, so look at the detrital zircons from these rocks. What do we see? All right, so basically we got 4 simplified stratigraphic sections from these 4 locales. We got Chino Valley, Mazatzal Mountains, Four Peaks, and Salt River Canyon. In Chino Valley area, we basically have a 1736 Ma pluton, the Williamson Valley granodiorite that intrudes essentially the Vishnu schist. I say that because the detrital zircon signature of this sample is basically exactly what we see in the Vishnu schist of Grand Canyon. And so I'm going to basically just go ahead and say it's pretty much the Vishnu schist, or at least it's an equivalent or a correlate. And unconformably overlying those, or actually the nature of that contact is not exposed, I believe, but I would interpret it to be unconformity based on this work. And so what we see in the Chino Valley quartzite is a bunch of 1700 Ma and 1800 Ma detritus. That is basically exactly what we would predict for the Yavapai province. So this, in all of these plots here, this kind of gray band is the 1700 to 1800 Ma time frame. That's the characteristic age of the Yavapai province. And so I'm seeing a whole bunch of detritus derived from the Yavapai province in that Chino Valley quartzite. If we go to the Mazatzal Mountains, we see something similar, where we've got a bunch of 1700 Ma or older, 1750-ish detritus that's present in those quartzites. In the Four Peaks area, we see the same thing, big 1700 peak here. And then in White Ledges, we see the same thing. We also see something different in the White Ledges formation. We see a lot younger detrital zircon in those rocks, which is a really exciting result from Mike Doe's work in 2012 that I'll kind of circle back to in a minute. All right. So there's a lot of data shown here, and how can we? I don't know. Maybe this is a simplification. Maybe it's just more complicated. But what I'm showing here now is a multi-dimensional scaling plot that I think illustrates a really important relationship here. So if we look at the detrital zircon signature of rocks from all over the transition zone and beyond into places like Grand Canyon and Death Valley, I think we can see some patterns. So basically, this plot over here is a multi-dimensional scaling plot that the way you interpret this is that samples that sit close to each other in space are similar in terms of their detrital zircon populations. If they're further away from each other, then they're more dissimilar. And so it's all kind of dimensionless, but that's how you want to interpret it. All right, and so the green samples here are all from the Yavapai supergroup and East Verde River Formation, right? Those unimodal metasedimentary rocks from either side of the Moore Gulch shear zone. Very distinctive off in that top right corner. In purple, I've got what we kind of call the Vishnu Basin. So it's the Vishnu schist and a bunch of other rocks that are part of what Holland and others called the Vishnu Basin in 2018. It's characterized by having a lot more Archean detritus. And so that's all shown in purple here. And then in blue, we've got in the light blue, we've got the Mazatzal quartzites, the Mazatzal province quartzites. And so what I would say here is that we basically have, the Vishnu schist signature, which is in purple, the Yavapai supergroup signature, which is way over here, and then the fact that the light blues of the Mazatzal province sort of plot in between those two tells us that, well, those sediments are derived from a mixture of purple and green, right? And then the darker blue is some work from the Pinal province, where there's sort of more of the actual younger 1.65 Ga detritus than in those rocks. And then the red here is got this significant 1.6 to 1.4 Ga population. We'll come back to that in a second. All right, so I would argue that this tells us that the Mazatzal quartzites are sort of derived from the Yavapai province, right? And that's what the detrital zircon data suggests. And we got the biggest peak is sort of the 1700 to 1800 population in most of these quartzites. All right, so now, excuse me, we're going to look at a pretty small area right here in the Moore Gulch shear zone. It's a 50-kilometer long structure. I must admit I've only seen a small section of it, but it's actually kind of tricky to get to. So went to this place, the Moore Gulch, and sort of said, all right, well, we'll do a couple of cross-strike transects and see what the rocks show us. And so we started in the Cherry Creek batholith up here, where we basically have fairly undeformed diorite in most of this swath up here. But as you approach these metasedimentary rocks shown sort of in brown, there's about a 100-meter wide border zone that's pretty foliated and lineated. So here, this field photo, this surface right here is kind of a corner. And so you can see the foliation in this granite and a pretty good lineation right on that foliation surface. So we got a nice, LS tectonite kind of texture here in the diorite that's up against those metasediments. And so several places we found really, really consistent stretching lineations, sort of, plunging to the northeast pretty steeply along that foliation surface that dips steeply to the northwest. So yeah, a couple of different places you see this really strongly deformed Cherry Creek batholith. So that's cool. All right, that's what I'd like a shear zone to look like, is have a bunch of mylonites in it. So that sounds good. As we kind of go away from that zone into the metasedimentary rocks, what we see is kind of a mix of schists and slate and phyllite. This is definitely deformed. We get some nice slaty cleavage here, and some really nice compositional layering. But one of the things that really stood out to me is as you walk from the contact with the Pluton towards the Moore Gulch fault, there's a lot more of a brittle overprint on these rocks the closer and closer you get to that fault. The main foliation is a schistosity or a cleavage that's locally parallel to compositional layering, which suggests that it's sort of a transposed combination of fabrics. There are folds, preserved in these schists that have the fold axes plunge to the northwest, and abundant stretching lineations are also consistently to the northwest, so sort of about orthogonal to the stretching lineations that you see in the mylonites on the edge of the Cherry Creek batholith. So we have this composite fabric. It's probably a combination of axial planar cleavage and a transposed, SM-1 sort of compositional layering. But As you go closer and closer to the Moore Gulch fault, the brittle overprint gets stronger and stronger until eventually you have this fault breccia, which is right at the fault here, location G. And this fault, the Moore Gulch fault or the Moore Gulch shear zone, not sure what to call it, juxtaposes rocks of the Yavapai province up against rocks of the red rock rhyolite group. And so that's been dated at 1701 plus or minus 2 by Cox and others in 2002. And you can see that contact in Moore Gulch itself here with the red rock rhyolite, appropriately named red rock rhyolite, to the right side of that picture, and then these rocks of the Moore Gulch to the left. All right. So it's just a summary of some structural data. Again, we've got this pretty steeply dipping, northeast striking, northwest dipping fabric that is, this kind of cleavage or myelinite. They're all kind of parallel to each other. Again, most of the stretching lineations are plunging steeply to the northeast, whereas the intersection lineations plunge steeply to the northwest. And collected some oriented samples and cut some thin sections and looked at the microstructures in the rocks, and basically none of the metasedimentary rocks gave good kinematic indicators. They didn't really have great stretching lineations, really strong intersection lineations. There were a couple of samples that I thought, well, there's kind of an alignment of micas here. I'll cut it and look, but just nothing in terms of kinematic indicators. They just kind of looked like your average schists. But these myelinites along the edge of the Cherry Creek preserve really nice kinematic indicators, consistently showing northwest side up. All right, so let's kind of recap. So we got our two models, and the para-autochthonous model says that, okay, we should have the two basements, right? The basement on the northwest and the basement to the southeast should be the same. I think the uranium, lead, and hafnium isotope data from the metasedimentary rocks and plutonic rocks strongly support the fact that they are, the basement of the Mazatzal province is the same as what's in the Yavapai province. The tridal zircon data also suggests that the quartzites were derived from the Yavapai province and deposited unconformably on top of that province. And then the third one here is not quite right. Moore Gulch shear zone, we would think, should have sort of a normal fault geometry. If the Moore Gulch shear zone is that deformation that we see on the margin of the edge of the Cherry Creek, then it's actually more of a reverse fault geometry. But either way, that works for us because it puts sort of deeper, older rocks to the northwest up and over younger, shallower rocks to the southeast. So I think that these data strongly support the original sort of model one, or the para-autochthonous model of Karlstrom and others, 1987. And so what that means is that as a suture, the Moore Gulch shear zone, it leaves you wanting more. Yeah. All right, so who cares? All right, what's the point? Why does this matter? Well, again, I mentioned some of this detrital zircon data from Mike Doe's work. Mike went to the Salt River Canyon and did a bunch of detrital zircon geochronology in the Yankee Joe and Blackjack formations that overlie the White Ledges quartzite. And in these rocks, he found heaps and heaps of detrital zircon. They're from the magmatic gap, or the tectonic gap of North America, where there's very few rocks, igneous rocks of ages between about 1,600 and 1,400 million years old. And so Mike found a whole bunch of this detritus in there, and that's important because, as you can see, this nice view looking right down at the contact between the White Ledges and the Yankee Joe, it looks pretty conformable, right? And so if those are in fact conformable, and all these other rocks are correlative, well, that would have serious timing implications for the deformation along these shear zones, right? Particularly the juxtaposition of different crustal levels across the Moore Gulch shear zone. So basically the there's a big detrital population that goes to about 1490 MA, and then those rocks are intruded by 1450 or 1430 or something. Ruin granite, I think, is the one that intrudes that. But so it's one of those 1400 MA granites that are all over the place. And so that kind of constrains deformation of the Moore Gulch shear zone potentially until after 1490 MA. That's interesting. And this gets the slippery slope gets even slipperier if we look at some of the other things that have been suggested about this origin. That many of these block-bounding shear zones that make up the Arizona transition zone, Berg and Karlstrom in 1992 proposed that these are conjugate shear zones, right? And so that they all accommodated bulk shortening during the Yavapai orogeny at 1700 MA, and if they are in fact conjugates, and my argument convinces you that the Moore Gulch shear zone might not have moved until after 1490, then that means that all these other shear zones might not have moved till 1490. So that's potentially a very exciting result. And then here's a summary of some geochronology of the AZGS's own Calvin Mako's work from his master's thesis in the Four Peaks area is very important. A really great monazite geochronology data set showing that most of the deformation and metamorphism in the Four Peaks area is probably Mesoproterozoic. And then some muscovite data from the sort of Crazy Basin area. This suggests that there's a pretty good 1450-ish signal regionally. So, all right, so why else does this matter? If we look at a little bit of a bigger picture, if we zoom out a little bit and we think about global scale processes, and we think about a little bit younger origins, a really great paper from a couple of years ago now in 2011 by Collins and others, they proposed these two sort of end member types of origins that we see. Sort of this kind of goes to the internal versus external origin thing that people like Paul Hoffman have talked about. But basically did a big compilation of hafnium isotope data globally and looked at these two different orogenic systems that have been active throughout a lot of the sort of recent part of Earth's history, and identified two different trends. We're in the circumpacific origin, the sort of external origin. We have this trend towards more isotopically juvenile magmatism, whereas something like the Eurasian kind of origin that would eventually evolve into things like the Himalayas has more of this shotgun blast where things get sort of more heterogeneous through time. And they attribute this to the fact that, okay, an external origin like the circumpacific orogenic system is sort of on the boundary of a big supercontinent, and it's primarily involving the sort of addition of juvenile kind of material derived from the mantle, whereas something more like these Eurasian orogenic system is assembly of all these sort of chunks of crust, like the Central Asian orogenic belt. It's like all these terrains and everything have been sort of mashed up in there, and so I've done a fair amount of compilation work of my own. I should note, most of this data, although they show it as being from a bunch of different places, most of that data really comes from Australia in this figure, and specifically it mostly comes from eastern Australia, where the Tasmanide orogenic belt I think is kind of similar to a lot of things about the Proterozoic rocks in the lower 48. We got about 1,000-kilometer wide swath that's accreted in 200 odd million years. And if we go over to eastern Australia and the Tasmanides, we got about 1,000 kilometers of rock that's been accreted to that continent in about 200 million years. So yeah, I did a bunch of compilation work years ago, and here we go. So here's the compilation. I would argue we kind of have a similar trend where we go from sort of more evolved signatures to more juvenile signatures through time. If we have a sort of paleogeographic context here, I've got the North America's turned on its head on the outside of this supercontinent, variably referred to as Columbia or Nuna. So it looks kind of similar, right, to this sort of circum-Pacific orogenic system. So I would say the bigger picture, I think that what we're seeing here is instead of the classic, island arc accretion and little terrains all getting collided, I would say that instead what we're seeing is primarily upper plate processes. So we've got a long-lived convergent margin, which is not something that anyone really argues about, but the nature of that margin is maybe what the argument is about. Are we closing ocean basins and colliding, Ringalia terrains, or is most of this happening due to, slab rollback and shallowing and rollback and shallowing, and primarily upper plate processes? And I would argue the latter, that most of North America was probably built as part of the upper plate of a long-lived convergent system. And that's cool, because what it suggests is that here in the Arizona Transition Zone, we have that record, almost continuous tectonism. And actually, it gets even more continuous if Steve Skotnicki's work in the McDowell Mountains, where he recently, a couple of years ago, documented a section of volcanic rocks that fill that tectonic gap, that sort of 1.5 to 1.6 billion-year-old MA time frame. Then it might be completely complete, which is really, really cool. But yeah, so those are my conclusions here, and so I would argue that the Yavapai and the Mazatzal province boundary is not a suture. I don't think that those terms are useful in the way that they're kind of originally intended, right? I think that the Mazatzal province is a continuum of the same process that formed the Yavapai province. I think that the Mazatzal province is essentially a younger and shallower continuation, essentially, of that whole thing. I think that this block-type architecture is probably something that formed in the Mesoproterozoic during what we now call the Pickery Sorogeny. And that, most of this happened in the upper plate rather than closing ocean basins all over the place. So with that, I'll end it and happily take questions and chat.
If you got questions, just raise your hand and we'll bring this around to you. We'll also have some people following us remotely, so we'll open the floor to them at some point.
Hi, thank you very much. It was very interesting. We took a field trip up there a few years ago, and I was wondering how you relate the extreme folding around the Shylock fault zone to your model. What's the age? What do you believe the age to be of that extreme folding over a short distance around Cleator that goes pretty much north-south along the Shylock fault zone? And then the other thing is, do you have a sense of the extent of the banded iron formations that are up there that are Paleoproterozoic? Did those at one time extend as part of a larger basin that was present but is maybe eroded away?
Let me answer the question about the BIFs. I've never seen those BIFs. So I've been in the Shylock area a couple of times. I never found them, so I can't really comment on that. But yeah, Shylock's really interesting. Dara and others in '91 essentially had a progressive deformation model, and they linked. Basically, there's a really slippery slope where the Dara paper establishes a progressive deformation model where basically all of the fabrics in this northwestern region could have formed as part of a single event in a progressive model. And the timing of that has long been attributed to, has been interpreted as coeval with the emplacement of the crazy basin Pluton. I'm just not necessarily convinced that that interpretation is right. So the interpretation is that the crazy basin is in place at the same time as the Shylock, and that's based on just fabric relationships in the Pluton compared to the wall rocks. And that's something that's open to interpretation. Right?
It looked like one of your earlier slides, it related Shylock to a younger event, maybe 1.4, but is it possible to have that extreme folding related to a kind of a suture where you get two bodies coming together, and instead of creating a dominantly faulted feature, that you get a lot of collapse of strata. I don't know if that's the alder group or what it is, but the extreme structural relief that took place in that area.
Yeah, I mean, there's certainly been a lot of shortening in the Shylock shear zone, but it's not clear to me that requires it to be a suture.
Okay.
In my worldview, if you're going to describe something as a suture, the rocks should be different on one side compared to the other, right? Because if they're the same on both sides, then what's it a suture between?
Thank you. Yeah. Great talk. Thank you very much, and thanks for showing up when you're not feeling well.
Thanks.
Thanks for the talk. That was pretty cool.
I got a question.
Yeah, I was going to ask a question.
Go for it, and then give it to John.
You're next, John. You're next.
Okay. Yeah, so with this fault that you're calling the Moore Gulch fault, whether or not it's reverse or normal sense of motion, I'm wondering how you get sediment derived from the Yavapai to make the Mazatzal in the upthrown block if it's being uplifted by this fault.
Yeah, easy. If the Moore Gulch shear zone goes up, yeah, here we go. The Moore Gulch shear zone, if the northwest goes up, you erode the crap out of all that, deposit it down here, and that's where the Mazatzal province is.
What about on the upthrown block?
Well, it's para-autochthonous, right? So, these rocks have been, moved around a little bit, but they're not exotic. Yeah, how did we get the Chino Valley there? It could have been eroded from anything, elsewhere. You go to Colorado, you see all the 1750 granites as well. I mean, there's plenty of rocks of that age to be eroded.
Okay, so externally derived. Okay.
Yeah, there's no shortage of 1700 MA rocks to erode in North America.
Okay.
All right, John, you're up.
Just, there are 25 people that followed this remotely, and so we'll have an opportunity to ask questions too.
Okay.
So you showed a multi-dimensional scaling diagram,
Sure.
and what I'm wondering is the variables that went into each of those dimensions. What did you have other than the hafnium isotopic composition of the zircons and the uranium-lead age of the zircons? And what other variables are going into those dimensions 1 and 2?
Yeah, this is actually just UPB, so this is not even including hafnium isotope data. So yeah, so the multidimensional scaling is a bit of a black box. You can choose as many dimensions as you want, right? You can make 3-dimensional plots. You can make 4-dimensional plots potentially. It parameterizes the different populations, and then creates this plot to basically show just like similarity. You don't need the same number of variables going in to get dimensions coming out.
So how are dimensions 1 and 2 separated from each other? I mean, I don't understand. What's different about them?
They're arbitrary. So it's literally similarity, right? Typically the way that you would do this, and I've kind of done it just because I know about the input data, but so basically you look at the pattern that is created here, and you can say, oh, okay, like dimension 1 on the x-axis, right? Is dimension 1 seems to be sort of increasing Archean component, right? Because these purple samples all have a lot of Archean detritus in them, and they're plotting over on this side. Whereas this corner over here is defined by just this 1.7 stuff. So it's a little black boxy.
Okay. No, that sounds good. All right. Thank you.
Other questions? Anyone else, or should we open it up to the folks that are following us from abroad, outside of Tucson? Jordan, you want to see if anybody would like to unmute themselves, ask a question?
Mike, I just unmuted myself, if you can
Yep.
hear me.
Hi, Steve. That's Steve Reynolds.
Yeah. So there's a really key relationship that everybody ignores because nobody knows about it. But in Phil Anderson's article in the Big Red Book, AGS Digest, he talks about the Brooklyn Peak area. And it's a really key area because what it has a conglomerate on the Mazatzal side of the Moore Gulch shear zone that contains big blocks of cherry tonelite. And then the conglomerate is overlain by the New River rhyolite, the 1.7 rhyolites. And so there's a couple big implications there. One, it requires that there's some early uplift along the Moore Gulch zone in order to bring the cherry batholith up to the surface, for starters. And then the other thing, Phil always thought that was such a clear tie between the two provinces. Phil Anderson likewise did not think that structure in the Moore Gulch shear zone was a suture, nor do I. It's a structure, it's a boundary, but I like it as the boundary between the Mazatzal and the Yavapai provinces, but it's a fuzzy boundary in places. But there's very few of those 1.7 rhyolites west of it. In fact, there aren't any. And once you get southeast of that boundary, there's a ton of 1.7 rhyolites. So I just want to point out that Brooklyn Peak area is a really key spot to kind of factor into the equation. And Phil Anderson's paper in the Big Red Book is the best place to look at that. And that's it.
Yeah, I'm familiar with that chapter. So I know of that conglomerate. I haven't seen it. I'd love to go check it out. Yeah, I think he also described the Moore Gulch as basically dying out as you go further east. And it becomes just a fault that's like centimeters wide between the Cherry Creek and, is it the Verde batholith or something? But yeah, so I'd love to get out there and see it, but it's pretty remote as far as I know. So when I had this was a COVID project actually years ago,
Yeah.
and I didn't have time or resources to get out there, unfortunately. But yeah, thanks for pointing that out.
Tell me
know
when
of-
you go
I
and
know
I'll
of
meet you
Phil's
there.
work. Sorry, go ahead.
Tell me when you go and I'll meet you there.
All right, sounds good. Yeah, it's a lot easier for me to get to these places now that I'm in Arizona. So a lot of breadcrumbs to pick up.
Yeah, and the other thing that Phil thought is as you track the Moore Gulch shear zone to the southwest towards New River, it just kind of fades out into nothing. And so that's another thing that tells you that it's not really that much of a suture. Phil thought that there were like alder group maroon slates on both sides of the zone, and if you go back and read Phil's stuff, he has some arguments that he thought, and it's mostly without too much data, but they're observations he's made, and he describes that Moore Gulch shear zone seems to go away.
Yeah. I mean, if you go to the southwest, it gets buried by like young sediments. So I don't know. If you go too much.
Yeah, but this
southwest,
is still by New River, where there's still lots of rocks exposed down by New River.
Oh, okay, yeah, I see.
Not the New River Mountains, New River, the little city.
Oh, okay.
Town.
Okay.
Yeah. Okay, that's it.
Is there anyone else who wants to unmute themselves? Mark, we do have a question here in the chat, and here it is. In the collision model, can the Slate Creek shear zone be the suture?
I think you still have the same fundamental problem that the rocks on either side of the Slate Creek shear zone are the same.
Okay.
So yeah, Slate Creek shear zone is kind of this area right in here, and okay, sure, maybe it's the suture, but then you got Hess Canyon and Four Peaks and all that stuff is still to the southeast of that structure. So you still have the same fundamental problem that there's rocks of the same, the same rocks on both sides of the suture. So I don't know how you call it a suture.
Any other questions from anyone? Mark, thanks a lot. That was a great talk.
Thanks, everyone.